Now that you've seen some of MIT's National Magnet Lab, I'd like to show you something really special. Alcator, MIT's fusion reactor. Now, the difference between a fusion reaction and a fission reaction is that in nuclear fission, you're splitting apart heavy uranium atoms. In fusion, the process that takes place in the Alcator, you're fusing together light hydrogen atoms. The advantage is no radioactive byproducts and a great deal of energy from some very simple materials. Hydrogen. There's enough of the right kind of hydrogen in 1 cubic meter of seawater to provide as much energy as 2,000 barrels of oil. We may be running out of oil, but we're not ever going to run out of seawater. That's the Alcator. Now, if there's no questions, let's go downstairs and take a look at another part of the National Magnet Lab. The experiment we're going to be looking at uses lasers as another method of heating up the plasma necessary for a fusion reaction. Be careful of the wires, by the way. There's a lot of high voltage going around here. The lab, by the way, was named after Francis Bitter, who was a pioneer in high-energy physics here at the Institute. He died in 1967.
Every year, nearly $5 million worth of research goes on at MIT and Alcator and other energy-related projects. Chemical engineers are working on getting more out of our dwindling reserves of fossil fuel. Nuclear engineers are developing better and safer fission reactors. And so it goes through every department of the School of Engineering. To coordinate these activities, MIT has recently established an energy laboratory where engineers and scientists, economists and city planners can work together on this important societal problem. Such a large-scale, concerted attack on a significant national problem is not a new concept at MIT. First, there was the radiation laboratory of World War II, from which came a steady flow of radar systems for use on land, at sea, and in the air. Its successor, the Lincoln Laboratory, has made further contributions, not only to our national defense, but also to our knowledge of the universe through its advanced computers and radio telescopes. The Draper Laboratory, named for its founder, Professor Charles Stark Draper, has made possible the guidance systems that have led man to the moon and back. The National Magnet Laboratory, where Alcator and other experiments requiring intense magnetic fields are underway. All of these were set up as special laboratories to provide a focus for the efforts of faculty and students from diverse disciplines, working together towards solutions to complex national problems. The director of the new Energy Laboratory is Dr. David White, Ford Professor of Engineering.
To try to put this into perspective, let's look back a little bit in the history and the way we have been growing in our use for energy. If I look from 1850 forward, I find an exponential growth in energy that by this point in time has a magnitude of something like 70 times 10 to the 15th BTUs, a very large amount of energy. If I look at population growth, which should have some correlation with this, I also find exponential growth. But in the period before the 1900s, population was growing faster than energy, while in the period after World War II, energy is growing at a much faster rate than population, and this is predicted to taper off, while present predictions are for this to rise. Here I'd like to show you a plot of GNP per capita and energy per capita for first the developed nations of the world, and we see the U.S. clearly the highest in both categories, but the whole Western world very high in these two categories, energy and GNP. The Russian bloc countries, communist bloc countries, are also very high in these two categories, and the developing countries, while much lower, are beginning to spread along the same line and moving rapidly in this direction. So we find that both the developing and the communist countries are reaching the same degree of energy intensiveness that is characteristic of the developed nations. As this continues, one can begin to ask the question, what does this mean in terms of the resources around the world? Let me focus on the question of petroleum, because this is the major energy source at this point in time. And let me here use proven reserves, stressing that proven reserves says nothing about total resources, but only that oil that has been located and is economical to produce at current prices. We find that the United States, which has 35% of the total world's energy consumption, with only 8% of the proven reserves. South America, 4%. Africa, about 9%, and 59% here in the Middle Eastern countries. This oil has to be consumed predominantly in the U.S., in Europe, and in Japan. Thus, there's very large flows of oil from this part of the world to the various developed sections. We find then that the developed nations of the world are drawing heavily on the natural resources of some of the undeveloped nations, resulting in economic issues in terms of transfer payments to these countries, political issues in terms of stabilities of supply, and non-trivial issues of the movement of the vast amounts of resources over the waterways to go to these distant points. In fact, there are other issues that we need to worry about. I mentioned the environmental one. For example, all energy consumed from fossil fuels must end up as heat. Presently, the average energy from the sun, which determines essentially the weather pattern of the Earth, is characterized by this graph. This little dot is that comes from energy consumption, about 1 part in 10 to the 4th of this. However, around Manhattan, the energy that's used to heat, air condition, transportation, industrial, is about 6 times what comes in from the sun. So while this amount of heat in a small region does not control the atmosphere and the climatic conditions of Manhattan, it certainly is having an influence. And as we see the kinds of growth that is going on both in the United States for energy use and in the world, one has to ask the question, does this kind of issue come up in the future, must it be dealt with, or is it never going to be more than a small local problem that we can handle easily? For this reason, MIT has established an energy lab to try to focus on these very long-range problems, to tie together the capability we have in systems analysis, and modeling, the capability we have in the developments of new technology, both in terms of cleaning up processes using fuels and developing new fuels, and how we might be able to conserve energy by doing our industrial tasks, our transportation in more efficient ways.
Sometimes computer results really surprise you. Part of the time it's because you haven't understood the system well enough when you designed the model that you were trying to describe. Other times it's because something new or something novel physically is happening. And those are the exciting times, because then you've understood something that you didn't understand before.
Professor Joseph Lassiter of the Ocean Engineering Department explains a computer model of the economic and environmental effects of opening up the New England continental shelf to offshore drilling for oil.
Feeling for how things work.
Well, I can understand building a model, a physical model like this ship, for instance, to see whether it'll float or what will happen in the wind, but I don't really understand a computer model.
Well, they're the same thing. Now, just like a man built a model of his ship before he built the whole ship, you know, why did he do it? Well, first of all, he wanted to find out if the ship would float. Mm-hmm. He wanted to find out how it would behave in wind and weather. He wanted to get an understanding about what he's going to be spending his money for. Well, before you start a large-scale development, something that's got environmental, economic, social considerations, you want to be able to try and anticipate, before you get involved with it, anticipate what's going to happen. So computer models are the same thing.
Yeah, but computers work with numbers and equations and things like that. How do you put in offshore oil development?
Well, probably the best way to describe that is through the model that we've been using to try and analyze offshore oil and gas development. Now let's look at this typical case. This is the Georges Bank area off Massachusetts. Now, let's just take a location of a potential, a hypothetical find. And from that hypothetical find, one could carry oil, say, to Point Tupper, Nova Scotia, down to Delaware, or someplace inside the New England region, someplace in southern New England, or maybe even all the way up in northern New England. Now, we don't know when or even if this oil will be discovered. But we have to have some idea of figuring out how much it's going to cost. So if I'm, say, moving the oil from the petroleum discovery to, say, southern New England, I might move that oil via pipeline or maybe via tanker. Well, I know that this discovery isn't going to change the speed of the tankers. Tankers have been making the same speeds for years. Yet, I don't know how far away it is. So if I take the speed, divide it into the distance, I'll get the time required for a tanker to go from here to here. If I know how many barrels are being produced here and how long it takes the tanker to get the oil there, I know how many tankers are required. So I'll try 100 or 1,000 or 10,000 different distances corresponding to different locations, and I can figure out how many tankers are required to move back and forth. So the computer model is just a bunch of these little things.
Yes, but it's a lot more complicated than just how many tankers you need, isn't it?
Sure, but that's the whole key to computer modeling. You have to make simple systems, little things you can understand with. Little black boxes where you know what's coming across one side of the black box and what's coming out the other side. You have a black box that represents the petroleum reservoir, a black box that represents the pipeline and tanker system that might service the offshore field, a black box that might represent the refinery on shore, another black box which carries the oil or simulates the carrying of the oil to Boston or to Providence. And unless you can build a system up of very simple black boxes, you just can't get started. In solid mechanics, you usually use the assumption that all the mass in some structure, like a table, is concentrated at something called a center of mass.
Right.
And then by pressing down on the center of mass, you can figure out what the application of force does to the table.
And for certain problems, that's perfectly satisfactory.
Sure, but as these problems get more and more complicated, you have to make up more little simplifications. But unless you get started, unless you make those initial simplifications, sell your ability to forget how complicated the problem is, you just can't get started.
Well, what does your model tell you about the possible economic impact on the New England region of this offshore oil exploration and possible discovery?
Unfortunately, that's the kind of question you always have to hedge on, because the whole purpose of building a complicated model is the realization when you start out with it, it's a complicated problem. So you have to give up some simple answers. Whether or not it means a lot to the region economically depends on several things. Whether or not foreign crude oil prices continue to escalate, whether or not the United States keeps the oil import quota, whether or not a refinery locates in New England, whether or not royalties and lease payments go to the federal government or to somebody in the region.
Right. What about the environmental effects, though, of something like this?
That's been one of the things that's been interesting and kind of surprising. If you look at the same kind of figure where you have unit cost, again, plotted as a function of gross barrels in place, I have two lines shown. If you look out about 3 billion barrels, you'll see a dashed line, which is a pipeline, and a solid line, which is a tanker.
Right.
Now, you notice that about 1.5 billion barrels, there's a crossover, so that pipelines are somewhat less expensive than tankers.
Doesn't look like there's a great deal of difference.
That's the whole point. We have reason to believe that pipelines are less environmentally costly, or possibly less environmentally costly than tankers. So that if oil and gas development did take place off New England shorelines, it might be in the region's interest to have the pipelines used instead of tankers by the private investor. So the region would encourage the private investor to use those things.
As we indicated earlier, much of the energy research at MIT goes into new technology, new sources of power that don't rely on coal, gas, or oil, or making more efficient use of the resources that we have. Now, making an electric generator a few % more efficient may not sound as glamorous as developing a fusion reactor, but it can have a more immediate effect on how fast we burn up our fuel. This is the cryogenics laboratory at MIT, where research is underway into a superconducting generator. Cryogenics is the world of super coal. It was back in 1946 that Professor Samuel Collins of MIT developed the equipment that made it economical to produce liquid helium on a commercial scale. I'm now with Dr. Joseph Smith, Professor of Mechanical Engineering at MIT, who's been using liquid helium in the development of a superconducting generator. And Professor Smith, we'd certainly like to know how this machine works.
Well, I would like to demonstrate the operation of an electric generator with this very simple model that I have here. We have a simple coil of copper wire which we excite with a direct current. This produces a magnetic field, an electromagnet if you like. If we bring this coil in the proximity of a second coil, we can generate electrical power by mechanical motion of this white field winding. If we rotate this field winding, we produce a voltage first in one direction and then in the other direction as we complete the revolution.
It's AC, alternating current, huh?
Yes, thus we generate AC power by the mechanical rotation of the field winding in the stator winding. One of the limitations of this type of generator, of course, is the heating of this white field winding. You can feel that this is already getting warm. If we replace this normal copper winding with a superconductor, we can completely eliminate this limitation due to heating of the field winding. And in addition, we can generate a much more intense magnetic field.
But to be superconducting, it has to be very cold, right?
Yes. To be superconducting, we have to be at only 4.2 degrees above absolute zero. In fact, we have a demonstration set up here of a superconducting coil in a dewar of liquid helium. And what we have is a superconducting coil. We are running an electric current through it, and we have a meter connected which shows the voltage across this superconducting coil with the current. And as you can see, there is no voltage. Now, if we lift the superconducting coil out of the liquid helium, it will warm up and go normal. And when it goes normal, we will see a voltage appear across the coil.
It doesn't take long.
Now, if we lower this back down into the liquid helium, we can cool it back down again, and the superconductivity will return and the voltage will disappear.
Always seems to me you're getting something for nothing when you've got current going through. There's no resistance and no voltage drop.
Yes, you are getting something for nothing very much in the same sense that a permanent magnet gets something for nothing. But of course, we have to live with this difficult low-temperature liquid helium.
And I should think that'd be even more difficult if you're trying to feed liquid helium into a field winding, which is rotating inside of a machine.
Yes, this is a difficult problem, and to solve this problem, we got together with the Electric Power Systems Engineering Laboratory here at MIT, and with the support of the power companies through the Edison Electric Institute, we undertook to build a 30 horsepower demonstration model that would show that we could rotate liquid helium and a superconductor in an electric machine. The success that we had with this first model led us to construct a 3,000 horsepower superconducting generator. The first step in constructing this generator was to build the